Hi everyone, welcome to AI Crack channel. This is Akash Gangbar and today we'll be studying Quadratic lecture 4 and this is the last lecture of Quadratic. So we'll be studying common roots and theory of equations in this lecture. So let's begin our lecture with the refresher example from the previous topic, that is location of roots. Okay. So we have the values of a for which the equation 2x square minus 2 times 2a plus 1x plus a times a minus 1 equals to 0 has roots alpha and beta satisfying the condition a is less than beta and a is also bigger than alpha, right? Now, first of all, if you observe this inequality, what we can see over here, you can see that alpha is not equals to beta and also not alpha. Basically, alpha is in between alpha and beta and not being equal to either of them, right? What does that mean? This means alpha and beta should be distinct, right? Because if they're equal, in that case, we cannot fit a value between them because they're equal, right? So they have to be distinct. Alpha and beta have to be distinct. And when they are distinct and also their roots of this equation, we can simply say that D should be positive, right? That is our first basic condition with the observation what we have made, right? Now, secondly, you can observe that the coefficient of x square is positive, right? So we don't have to bother about downward facing parabola. We just have to bother about the upward facing parabola because the coefficient of x square is given as positive over here, right? So that's our second observation. Now, third observation is when we have been given that D is positive, we can have these three cases. A can be here, A can be somewhere between the roots alpha and beta, and A can be here, right? When we are just considering this condition, these three cases are possible, right? Now we have to eliminate this one and this one. Why? Because we have to have A between alpha and beta, right? Now, what is the major differentiator between these two and this one? What is the major differentiator? We can see that over here, f of A is positive, right? In both these cases, f of A is positive. In this particular case, f of A is negative, right? So our second condition would be f of A should be negative. That should be a second condition. Okay. So what we have got these two conditions for this particular question. Now understand one thing, when we are saying A is between alpha and beta, also f of A is less than 0, right? When we are saying these two things, what do we mean? We inherently means alpha and beta should be distinct, right? Because if we take this case or if we take this case, in both of these cases, we can always say that f of A is either going to be 0 or positive, right? It cannot be negative. So when we are saying that, when we're applying this condition, f of A is less than 0, it automatically includes D should be positive, right? Because that is only possible when alpha and beta are distinct, right? When alpha and beta are distinct, this is going to be possible, or vice versa. If this is possible, then we can say that alpha and beta are going to be distinct. That basically means this condition is encompassing this particular condition as well. This condition is going to be superset, but final answer would come from this only and from this only. It won't include these conditions. And now let us move forward with this question. So our one and only condition is f of A should be less than 0. Okay. And now since we know that our one and only condition is f of A is less than 0, so let's apply this condition. So we'll be getting 2a square minus 2 times 2a plus 1a plus a times a minus 1 less than 0. Okay. So we can take a as common. We'll be getting 2a minus this becomes minus 4a minus 2 plus a minus 1. This is less than 0. Okay. So this becomes a times this becomes minus a and this becomes minus 3 is less than 0. Basically what we have got, a times a plus 3 is positive. Okay. That gives us the range of a as a belongs to minus infinity to minus 3 union 0 to infinity. Now even if you want to check d as positive, I can still say that when we intersect both of these conditions, you will still get this answer only, right? Because this is going to be superset and this includes all those conditions which are already there in this one. Okay. And now let us move forward with common roots. So we have two cases, either both roots are common or one root is common, right? So let's first understand when both roots are common. Okay. So let's have the basic equation. We have ax square plus bx plus c equals to 0. Now, when we are saying both roots are common, what do we mean? we mean that the other equation is going to be the same equation, right? Essentially it's the same, right? Unless the equation is an identity, we can simply say that the other equation is also going to be the same, but there can be certain conditions which we'll see, right? Okay, so other equation would either be ax square plus bx plus c equals to 0, or it can be multiple or a fraction of this current equation, right? So it can be either 2ax square plus 2bx plus 2c equals to 0, or it can be ax square by 2 plus bx by 2 plus c by 2 equals to 0. Either ways it's possible. Okay, and now the real question is, can we find out any relation between this and this equation? Yes, we can do that. So if we write down the ratio of coefficient of x square, that would be a upon 2a, right? If I write down the ratio of coefficient of x, that would be b upon 2b. If I write down the ratio of c constant terms, that would be c by 2c. Now if you look at them closely, you'll see that all these ratios are nothing but 1 by 2, basically a constant number k, right? It can be 2, it can be 3, so basically a constant number k comes out of the ratio of these terms, right? So if I have two equations, a1x square plus b1x plus c1 equals to 0, and the other equation is a2x square plus b2x plus c2 equals to 0. Now when we are saying that when both roots are common, a1 by a2 equals to c, b1 by b2 equals to c1 by c2 equals to some constant k. So when this is being satisfied, we can simply say that both roots are common, right? Very simple. And now let's talk about the other case when one root is common. Okay, so we have these two quadratic equations, a1x square plus b1x plus c1 equals to 0, a2x square plus b2x plus c2 equals to 0, and alpha is a common root. So when alpha is a common root, it's going to satisfy both the equations. That's why a1 alpha square plus b1 alpha plus c1 equals to 0, and a2 alpha square plus b2 alpha plus c2 equals to 0. Okay, now we have got this condition. Just like we have got this condition in the first case, we have got this condition in this second case. Okay, how did we get this condition? Although it seems very complicated, but how did we get this condition? So what we'll be doing, we'll be first using the elimination method to find out this condition, and then we'll use a shortcut. Okay, so for elimination method, we'll be treating alpha square and alpha as two variables, and then we'll eliminate them. Okay, so for first equation, I'll be multiplying a2, and second equation I'll be multiplying with a1. Okay, so what we have got, a2 a1 alpha square plus a2 b1 alpha plus a2 c1 equals to 0. Okay, and over here what we have got, a1 a2 alpha square plus a1 b2 alpha plus a1 c2 equals to 0, right? Now if we subtract both of them, what will be getting? We'll be getting alpha times a2 b1 minus a1 b2 equals to a2 c1, sorry, a1 c2 minus a2 c1. Okay, so alpha would be a1 c2 minus a2 c1 divided by a2 b1 minus a1 b2. Okay, we have got this value of alpha. Now if you look at this part of the equation, we'll also get the same value. We have minus alpha over here, and we have a1 b2 minus a2 b1, but in the denominator over here we have a2 b1 minus a1 b2, right? So if you remove this minus alpha from here, you will get the same value over here. Okay, and similarly you can eliminate alpha and you can find out this part of the equation, and once you have done that, you can find out this condition, that is a triplet. Okay, so that was a very crude method to find out this triplet condition. Let's try to understand a basic method or a shortcut method to write down this condition. Okay, so what we'll do, we'll start with alpha square minus alpha and 1. This you have to remember, or what you can do, you can take the reference from the equation itself. So for alpha square, you can take the reference from here. For minus alpha, you can take the reference from here with a negative sign. And for 1, you can take the reference from here because we don't have any alpha over here. So that's why we have taken 1. Okay. So now once you have written that, we have to find out the denominators, right? So for this one, what we'll be doing, we'll be hiding these terms having alpha square. We'll be hiding these terms with the alpha square. Okay. Now we can write down a determinant over here. So determinant would be b1, b2, and c1, c2. Okay. Now similarly for minus alpha, we'll hide these two terms and we'll write down the determinant. That would be a1, a2, and c1, c2. Right. And for this constant part, for this one part, will hide these constant terms and will write down the determinant. We'll be getting a1, a2 and b1, b2, right? Now if you open up this one, we'll be getting alpha square upon b1 c2 minus b2 c1, right? Same as this one, right? b1 c2 minus b2 c1. So this you have to remember. This is a basic shortcut method to remember this particular condition, or else you might forget if b2 c1 is there or b1 c2 is there, which is coming first or which is coming later on. So you might forget that. So that we have devised this shortcut condition. Okay. And now let us solve this problem. A value of b for which the equations x square plus bx minus 1 equals to 0, x square plus x plus b equals to 0 having one root in common is. Okay. So let's say alpha is a common root. So we'll be getting alpha square plus b alpha minus 1 equals to 0 and alpha square plus b equals to 0. Okay. Now let's write alpha square minus alpha and 1 over here. And we have to find out these denominators. Okay. Now for this one, for alpha square, we'll be hiding this column and we'll be getting b1 from here and minus 1b from here. Okay. For minus alpha, we'll be hiding this one and we'll be getting 1, 1 from here and minus 1b from here. Okay. And for this one, we'll be hiding this constant column. So we'll be getting 1, 1 from here and b and 1 from here. Okay. Now these three should be equal. Okay. So this comes out to be alpha square upon b square plus 1 and this becomes minus alpha upon b plus 1 and this becomes 1 upon 1 minus b, right? Now what you have to do, you have to find out alpha from here and you have to find out alpha square from here. You have to square this one to use that value over there, right? And then you'll get the answer for b. That's a very simple problem, right? There is no problem in that. And now let's solve this problem. If it is known that a, b, c are real and the quadratic equations ax square plus bx plus c equals to 0 and 2x square plus 3x plus 4 equals to 0 have a common root, then a is to b is to c is equals to, right? In this case, it has been given that it has one common root. But if you observe that d is less than 0 for this equation, we know that complex roots occur in pair. And when we are saying it has a common root, which is a complex root, basically this also has d less than 0, right? Because it has one common root and it's complex, right? And complex roots occur in pair. So basically both roots should be in common. Both roots should be common. So this equation essentially is the same as this one, right? So a is to b is to c comes out to be 2 is to 3 is to 4 only, right? Very simple. So today's lecture was still here only, and this is the end of quadratic. And from next lecture onwards, we'll be starting with progressions. Okay. So let's meet in the next lecture. Thanks for watching.